Okay, I am pleased to introduce Tom Hales, who will be telling us about formal abstracts in mathematics.
I'd like to thank the organizers for this chance to talk about formal abstracts, and most of my presentation will be on controlled natural language. So this is part of a formal abstracts project. I'll say a word about their sponsors. Just to give you the context of where I'm coming from, I've been doing formalization of mathematics now going on 19 years. So if Jeremy, I know, has been doing formalization about that long. I don't know if anybody else in this room, we're probably the oldest, been doing it as long as anybody. So it started with sphere packings, proved a theorem, couldn't get it accepted for publication, decided to get rid of referees for mathematics by replacing them by a computer. That still hasn't happened, but it's still an ambition for the future. And eventually, a big group of us did formalization of this theorem about sphere packings inside the whole light theorem prover with a few parts in Isabelle. And this was a big project, about 500,000 lines of proof scripts in the whole light proof assistant. It involves formalization of a large body of mathematical text and formalization of some fairly significant pieces of computer code. But that's finally in the past, fortunately. So formal statement is at the top, saying if you have packing, its density is at most that of the face-centered cubic packing. So part of this project was proving nonlinear inequalities in an automated way. And for that, we actually needed a cloud computation, so that one piece was not done on a single laptop, but all the rest can be done, checked in about a day on a laptop. So that's my background. And then in 2014, at the International Congress of Mathematicians, the president of the International Math Union, Ingrid Debices at the time, organized a session on the digitization of mathematics. And from the point of view of mathematicians, they would really like to move everything in the direction of using computers in a much bigger way. I was at the session, and of course, Lean users all want to say, okay, all mathematicians should just start using Lean. But I didn't speak up just because from my own experience, that was one theorem taking all those years. I can't really recommend that all mathematicians do that. But this discussion really got me thinking, what is it that we can now do that would build a bridge between current mathematical practice and what's happening in the formalization community. And my concrete proposal is what I call formal abstract. So just from experience, it really takes a lot of work to do proof formalization, but just to get mathematicians feet wet, let's start writing down formal statements of theorems, formal statements of both definitions and theorems. And so I said formal abstracts should give a statement of the main theorems of each published mathematical paper in a language that's both human and machine readable. And then we have links from the theorems to the definitions, and everything's grounded in some foundational system like a proof system. So that was the proposal, and I wasn't really planning to do this myself. It was just a slide in a presentation, but then after my presentation, some people got excited and said, well, you should really do this. This slide is another slide from that same presentation, just saying, you know, this is really directed to mathematicians more than computer scientists, but it really matters how we move from doing mathematics on paper to mathematics on a computer. If we do it in a sloppy way, then mathematics as a whole will suffer, and by extension, science as a whole will suffer. So we should really design this in a way that really brings higher standards to mathematics. So I don't think there would be any disagreement about that in this group. So just some of the benefits. We want to eventually bring benefits of proof assistance to the general mathematical community, set standards for the sciences, set the stage for applications to ML in mathematical proofs, move math closer to the computer. So part of the motivation is just looking how this formalization project in sphere packings has been used since then. This is a paper by Kolesik and Cholet and Segedi. So these proof scripts inside the whole light proof assistant are now being used in machine learning projects. For instance, you want to teach a computer how to do proofs. It's easiest to start with a formal proof rather than an informal proof. So one motivation is machine learning. So I've been involved with a group in Hanoi at Ting Long University. Some of them have been here at the conference, and a number of people have traveled with me to Hanoi to work with this group. So it's great that a lot of us can be here together today. So now I want to turn to controlled natural language, and I'll try to give a lot of motivation. Some good questions came up this morning with Peter Kupke's talk, and I hope we can continue the discussion of those questions now. This is basically the same example that Peter gave. It's just copied from him. So of all of the examples of mathematics that I've seen written, you know, I show mathematicians samples of Lean, I show them samples of whole light, of Coq, and so forth. And most mathematicians find these samples pretty unreadable. In fact, I do tests with Lean users. I show them a Lean proof. I show a Lean proof to a Lean user, and I say, what is this proof about? And, well, maybe they can read the theorem statement and tell you what the proof is about. But I'll say, you know, what's the gist of this proof? And it can be very hard to look at a Lean proof and say what the gist of the proof is, you know, what method was used or something. And, you know, the person will tell me, well, I know it's a theorem because Lean checked it. But it really, in a lot of cases, the proof scripts are not so useful in guiding mathematical intuition, and so they might not be too valuable in you know, teaching us how to think about mathematics.
We could improve on that without changing the system. I mean, we could write tactic proofs in a more readable way.
Well, yes, and I mean, one interpretation of what I'm doing is exactly that, right? Because we can improve, yes. So here's an example. A controlled natural language is a language that's based on a single natural language, such as English, has a restricted syntax and semantics that are precisely spelled out. Speakers of the natural language, if it's a math-controlled natural language, you'd also need to know math, but speakers of the natural language can largely understand the controlled natural language, at least intuitively. The definitions intended to exclude artificial languages and programming languages. So I sort of see the picture as, we've got computer science and programming languages here. We've got math here. We've got maybe controlled natural language is something that I'm intending as a bit of a bridge between the two. Simone made the comment that we're going in the wrong direction. Simone, I see, is sitting here. I'm sitting over here, and I say we're going in the right direction. I intend this as sort of a bridge technology, something that might be a gateway drug for mathematicians on their way to lean, but there might be reasons to actually use this, and then eventually, if we have the lean system, like it was suggested this morning, this extended syntax might eventually all be part of the lean system itself and implemented in lean, but for now it's not. So some of the lessons that I take from Peter Kupke's example. So English has high redundancy. And what that means is that a lot of the grammar of English is not really necessary when you extract, for instance, the first order logic content of a sentence. You can really throw a lot of things away. And so that's really, really exploited by the design of the controlled natural language. You do not have to be a real expert in linguistics to make this work. It's really clever how, it looks like you're reading English, but, and it looks like it because it was written by somebody who knows English. But a lot of what you write is not really necessary for the extraction to first order, or in our case, the lean theorem prover. Realistic examples exist now, and they work, okay? So that's what Peter Kupke has shown us. And the thing that really changed my mind was that this is implemented in a really relatively small amount of computer code. So it's about 7,000 lines to do this system that gives a realistic English text for mathematical proofs. 7,000 lines or so. It's nothing, right? So it's really possible to do these things. It's not that much code. Let's give it a try. Let's try to make a controlled natural language whose back end is the lean theorem prover, and let mathematicians write in that language with a precise syntax, precise semantics. Same benefits as I mentioned before. So long-term picture, you might imagine a mathematician writing a paper in tech saying, I don't want to do lean because it's too hard. And then we go and say, well, guess what? This tech file that you wrote is actually a lean file. You've done what you need to do. Thanks for the formal formula abstract. So what I'm doing is I'm taking the Fortol, Naproche, SAD work done by Peter Kupke and his students and all the people before that. I'm modifying it. So the target of that is first order logic. I'm modifying that so that the target is the lean system, calculus of inductive instructions. So that's the basic idea. I want to use tech, so I'm throwing in all the syntax of lean. I'm throwing in all the syntax of tech. Well, not all of it. I'm throwing in all the syntax of this controlled natural language fortile, and then I throw them all together and I identify sort of the common parts, and that becomes a new grammar. And then you write texts in this precise language, and you sort of eliminate the tech and the controlled natural language parts, and what you're left with is something in a lean language. So I'm not proposing that we take mathematical formulas and expand them out into words. What I'm proposing is that we have texts that are written in English, where there are formulas written with the syntax that we're used to using in mathematics, maybe pieces of code using the syntax that we're used to using in lean. We have a document that contains words and formulas and pieces of code, and then through the precise semantics of that language, it gets expanded into something that's purely lean. Okay, so that's the product. Yes?
You expect a user of a person to edit the lean code after the fact, or that the lean code would be perfectly a perfect rendering of the natural language input?
No, I do not expect it to be a perfect rendering. So here again, it depends on what we're trying to optimize. So a lean programmer like you probably will not want to write lean code inside this language. Math library people, are writing certain definitions in a very careful way to get all of the things just right. When you do the automatic translation, it's just not going to be as nice. It's just not. But you might hope to have theorems that somehow prove the equivalence of the optimized versions with the automatically generated versions of things. So that's what I might hope for. Yes?
The auto-generated stuff, well, the auto-generation depends on having hooks from earlier, right? So if you want to use something in natural language, you need the natural language hooks. So it's hard to interface with an existing lean library that was done manually, not using natural language. Is that right?
Here again, I mean, the automatically generated thing is not going to give you the lean math library, right. but you really can hope for theorems that link the two. So just a word about the grammar. It's not a context-free language. Context-free language be described by fixed finite sets of terminal symbols, non-terminals, and production rules. But it's almost context-free. The only difference is that you can add new production rules to certain non-terminal systems to extend the language as you're building this up with new mathematical definitions. Word about the language. Again, it's the controlled natural language is done with some really clever tricks that make it look like you're doing English when it really isn't. When you're really not using that much linguistics. So, for instance, the language has full support for adjectives, nouns, verbs, conjunctions, formulas, and code. But at the same time, articles, the, and only partial support in special context, prepositions, only partial support. Adverbs are not supported. And you get around these things with certain tricks introduced into the controlled natural language that allow you to introduce stock phrases and things. So like they're not adverbs, but if you take a word like totally, you can have totally bounded, totally disconnected, and so forth as set phrases, and so they can still be introduced into the language. So maybe I'll break for just a moment and show you kind of what it looks like in practice. So here I've got a text file. So this is all written in, so this is just sort of a 30-page test file that I'm using. This is all written in the controlled natural language. So this can be parsed in a precise way. Right now I've got it so it reads the file according to the grammatical rules. It produces a syntax tree for everything that's written, but it isn't translated all the way to lean. So that's still work that needs to be done. But I hope that you find this fairly readable mathematical text. I do a bunch of things down. I put groups and rings and different things, and I sort of end with statement of the zero theorems. This is what the text looks like. So the question is, what do you have to type to get something that gives a nice PDF on the one hand, and something that can be parsed as a controlled natural language on the other hand. And I don't know if this is big enough for you to see. But this is what the text looks like. So it's really not that different from what you might type as a mathematician. But the claim is that this can be read in some precise mathematical way. The key, so there's a whole process that's followed to go from the text to the controlled natural language and so forth. The key is really the TEC macros. I hope everybody here knows something about TEC, but that you have control sequences and TEC macros. Those are, each control sequence has its macro expansion, so sort of a macro expansion language. What I do in the TEC is I have a dual expansion system. So everything has the usual TEC expansion, but every control sequence has a second expansion in terms of the rigorous semantics of the symbol. So if it's processed by the TEC engine, it just gets rendered in the usual way as TEC. But if you expand by the secondary meanings of the control sequences that are giving the semantic meanings, then you get the controlled natural language instead. So just running a file, for instance, so this is the TEC file. I hit return, and it just went through the TEC file, that 30-page document, and generated the controlled natural language, which is stripping all the dollar signs and spacing and all the things that are irrelevant for the semantics and leaving the controlled natural language. So we get, and so then this is in the precise syntax of the controlled natural language, which is then parsed at the next stage. Okay, so that's what we're doing. So how do we deal with things like inflection? So fortunately, there isn't much by way of declensions and conjugations in English. It makes it much easier. I've got a main inflection is just adding an S to words. In the controlled natural language, there are things called words that sort of correspond to English words. There are identifiers that are sort of identifiers as you see in computer science. And then there are things called variables, which is sort of a distinct lexical class that has particular meaning inside the controlled natural language. So something like a single variable B would be a variable and not an identifier. So words are case insensitive. So if you're using them in a sentence, you'll capitalize the first word of a sentence, and the controlled natural language knows how to deal with that. But also, there's a desingularization algorithm that I added that like strips off the S's at the end of words. The reason I desingularize rather than pluralize is that adding S's to a word doesn't have a fixed point, but taking S's off the end of words does. And so I desingularize the words to put them in a canonical form. It leads to a few weird results, like series desingularizes to Siri, but that doesn't matter as long as you don't try to use Siri as a different word inside the text. Yes?
Don't you change the meaning of a sentence by turning a name from plural to singular?
So in the system, if two words have the same desingularization, they are synonymous. Okay, so that's something to keep in mind in the controlled natural language. But identifiers are, completely case sensitive, and there's no process applied there. But again, there's a great deal of redundancy in English. You can really reconstruct the precise meaning from the canonical form of the word. And then there's a synonym mechanism inside the language that you can use to declare, like if you have tetrahedron, tetrahedra, special plural forms and things, you can declare those as synonyms. Why do I think mathematical English is a good idea? Well, for one reason, why have people been giving talks in English at the Lean conference? We use English as a language of communication in mathematics. It has a long history, natural languages. We learn in very early childhood. Words are meaningful to us in a way that symbols are not. I think it would be a big mistake to try to ban English from mathematical communication. Rather, what I want to do is take mathematics as it's currently communicated and make it possible to really make that precise. Just to give a trivial example, which of these is more precise? Well, if we define or to be this, then they're equally rigorous, but the word or will have a bigger reader audience than the symbol. So if we're trying to reach a wide audience, this probably might take the same number of keystrokes in Lean as this, but here's a single symbol. So we have maybe more compression here, but more meaning here, but equal levels of rigor. So Knuth, who's thought long and hard about mathematical notation, really thinks it's a mistake to write mathematical texts using pure symbolic formalisms, unless, of course, you're specifically doing mathematical logic or something where the structure of the equation matters. Now, some people find the equations easier to read, some people find the words easier to read, but I propose that we allow both. Yes?
So when I was making the natural number game, when I started doing basic logic, I realized that I couldn't get away from this V to mean always, because it was always there. And I realized that the moment I've done that, all of the high school kids in the world are now not going to play this game.
No.
And they were people that I'm always interested to get school kids in, but you don't learn it at school, so already they're gone. Genuine problems.
So I've written down a precise grammar. I wrote it down, and there's a Menhir parser generator tool in OCaml that I used. The lexing is done, again, by a tool in OCaml. The implementation builds on the parsing for whole light, which has a parser combinator library, and I extended that parser combinator library to do the parsing of this language. And as I mentioned earlier, currently it goes as far as a syntax tree, but we don't go as far as, so we want it to go all the way to lean. I wrote the syntax with lean in mind, so I put in inductive types and mutual inductive types and all the things that lean users are going to want to use. But you can also use the tech control sequences, so you can have integrals really written with the integral symbol in tech and have that expand out using the semantic meaning of the control sequence into the integral inside lean and so forth. So that's the idea. This is just a summary of how the tech to control natural language works. You can write arbitrary text code in your file, but then I have a special environment for the controlled natural language, and everything, excuse me, I'm losing my voice, everything inside that environment is read as tech, as controlled natural language. So if you have, and it has to be written then in a very careful way according to the syntax of the grammar, but then you can write arbitrary things outside the environment. Some people ask, why don't we go the other direction, take lean and translate it to English? I think that's a good project too. That's not what this project is doing. From my point of view, I'm doing it in the easy direction, and somebody else can do it in the hard direction. I say easy because English has redundancy built in, and you can have people write in fluent English and then throw away the grammar that you don't care about, but go in the other direction. Unless you work really hard, it's going to look like computer-generated English, because it is computer-generated English. So you can do that, but I just think it would be hard to do it in a convincing way. So I'm departing from lean in a few ways because I, sort of the same philosophy as lean 4, as long as we're making changes, why don't we make the changes we want to make? But at some point, I plan to sort of bring this all back together. So right now, I haven't put in universes. For instance, I mean, there are different policies that people use for universes, like we'll always try to do it at the lowest level, or we'll try to do it polymorphically, or we'll try to do it in the categorical way, where morphisms between objects of the same type have the same universe level. So there are different policies that get used. So I'm hoping that for a lot of what we can do, we can just sort of set policies and have it be worked out automatically, but that's just wishful thinking at this point. And my postdocs give me examples of where you really want to care about universal levels. I haven't put in a tactic language just because I'm really focused on formal abstracts of writing definitions and theorems, but I have sort of included the simple proof language that's currently used in Fortol. So you can sort of generate statements, you write a proof and generate statements, but there's no reason that those statements would glue together logically to make a valid proof inside Lean. We're using ASCII, but that's just a convenience. We've got some syntax restrictions. For instance, all parentheses must match. But since we're allowing pretty arbitrary tech control sequences, that's not really a limitation because you can just do it in tech and do what you want there. Okay, so that's maybe an overview of what it is that we're doing. There's still an incredible amount of work that needs to be done. I mean, the biggest piece is still translating from the syntax tree over into Lean pre-expressions that get accepted by the Lean system, but then also in terms of tools, just making it easy for users to write in the controlled natural language. The Hanoi group has been doing examples without any documentation, so that's been pretty encouraging that they've been able to get some examples of mathematical text to work, but we need documentation, we need editor support, we need all the tools to go along with this. So I'll stop there. Thanks.
We have time for questions. Yes, Siva.
So I've been noticing that we can all basically agree that Lean has a backend for peer improvement in the sense that we kind of like agree on what our foundation ought to be and what we can like here improvement. But the real disagreement happens like in the front end where we all disagree on like the syntax to use. Some people want to use controlled natural language, some people prefer manual expressions. So do you think it would be worth investing in some kind of technical infrastructure for Lean where Lean really becomes like this headless server where you issue peer improvement commands to, and there are like multiple supported front ends for it in various languages. And I mean, this is doable, but really the hard part is importing like error messages from the back end into the syntax that you usually use to for that particular front end. Like, to give you an example, like, we have like Lean, the permanent language as a front end. We can see error messages. And there's also like, if we had like CNL as a front end for Lean, like the error program, you could also see like proper English language error messages highlighting like English text, saying this is where you went wrong. I think that would be like an interesting direction.
So I agree. So that's one other thing that we need to work on is our error messages. You know, in terms of what people want to do with Lean 4, I'll leave it to others who are more an expert than I am. But yeah.
Let me just add a comment that I think the more interesting direction is, what I like about the controlled natural language is that it is foundation agnostic. So there's nothing that ties it to Lean. So one can just as well translate that to other foundational backends. Really good.
Okay.
Yeah, Tom, do you have comments about how other aspects of formal languages or verifiers influence readability? So like one example that was mentioned in passing is the procedural style versus the possible declarative style that we use in anything.
Right, so there's the, of course, the Mizar system that makes some attempt to make proofs readable. There's a bit of history that I sort of skipped, and maybe Frick can give more details than I can, but like the math vernacular, there have been other attempts besides, the foretold approach system approach, like FL, which is a project by Neumeier that is using sort of a graphical representation of mathematics, but again, based on natural language. There are things like Izar in Isabel. So there have been, I think, a lot of different projects, and I picked Fortel just because I found it, well, I show it to mathematicians and they say, oh, this looks like what I would write as a mathematician, and I haven't had that experience with any of the other systems. So there was that factor, and just the fact that it was implemented in so few lines of code. I thought, let's go with the easy thing that works well.
Presumably some of these directions are somewhat independent, and you could add other ideas to it.
No. Mario.
Have you tried to write a presentation which is sort of designed to, let's say, present like a full mathematical work where maybe you want to also have explanatory notes in it? For instance, if you were to present one of those CNL documents as a journal paper, it would probably be criticized on the ground that it was a little stated. Maybe you aren't stating things in a very why are you using so few words and using them over and over again? What could you do to improve the situation where mathematicians would feel comfortable using this and still being able to test?
Well, my feeling is the language is pretty expressive now. I mean, we don't have pronouns, but we have variables, and you always use variables instead of pronouns. I don't know. I'll just try to get this to work, and then we'll see how to improve it. I should say there are a lot of other projects that have started up in this last year as well. Chad Brown is working on a version of controlled natural language with target set theory. I think Florian Rabe and Kalisic are starting another project in controlled natural language, and so it may be that we have several different experiments to choose from in this space.
What can you at least like have a paragraph, let's say, that are not part of the CNL?
Sure. Yeah, I should show you the document, but anything inside a remark is not part of the CNL. And the way I've got it set up now is everything in blue in the document is informal text. So you can always leave the CNL environment. That's one thing you can do. But even within the CNL environment, you can mark something as a remark or as a parenthetical, and those are just ignored in the parsing.
Well, okay, I think that's all the time we have for questions. Let's thank Tom again. I have more minutes until we are scheduled to depart to Kevin's talk.
I have a question.
Oh, okay, we have time for another question.
I've left my clicker in the hotel. Does anyone have a clicker?
Yeah.
You can borrow Rob's.
Thank you.